Well, for those of you already here, welcome. Well, for those of you already here, again, welcome. We still have 2 minutes to our official start time. What I see on my laptop, and then we'll give it like an extra minute for people to roll in. Welcome, everybody. We've still got about a minute till our official start time. Well, and I see that we're at our official start time. So we'll give it one more minute because people are still rolling in, I see. But welcome for those of you that are already here. Glad you could make it. It's a beautiful day here in Texas. We've had like a cold wave. It's like only in the low 90s. So like I may have to go find my winter jacket if it keeps up like this. So we're going to give it one more minute for people to, because people keep rolling in, and then we'll get started. Hope it's a beautiful day wherever you are. Okay, wow, the people counter keeps going up. Okay, I'll give it maybe one more minute and then we'll get started. Okay, we'll go ahead and get started now. Well, welcome again. I'm Mike Riddle and president here at INCAP America, and today we're going to be talking about Sag and Tension Theory 101. Last month, I was talking about sag and tension calculations for OPGW, and I had effectively jumped into the middle of a topic and then caught myself and asked the question, should we go back and look at some basics? And the feedback was strongly yes, please do that. I'm concerned that this might turn into a case of be careful what you wish for because I went back to the very beginning. Uh, we'll see how it goes. I'm also concerned that I might go a little long today. Again, we'll have to see how it goes, but thanks for joining me. So this presentation is RCEP compliant. So this just means that we've met the standards of their continuing education program, and that in turn means that you can earn credit upon completion of the program. And I'll tell you how to do that at the end of the presentation. Then you'll get continuing education credits through RCEP. This does not mean that they endorse or agree with or approve of any of the content here. Just means we met their standards. So today we're going to look at the basics of sag and tension theory. We're going to look at what sag is and the low point in a span. We're going to look at what tension is. We're going to look at the everyday relationship between sag and tension and the three exceptions to that relationship. We're going to look at what creep is and how it changes sag and tension over time. We're going to explain what a catenary is and how it attaches to this topic. Likewise for a parabola and why you might want to use one versus the other. If you're using the parabola, what kind of error you're looking at getting. We're going to look at the three big sources of sag error. And then I want you to understand along the way, we'll see the difference between elastic and plastic changes in conductor and how that affects sag and tension calculations. So the agenda, we've already done the introduction. We've discussed the learning objectives. Now we're going to hit the presentation. Please hold questions to the end and please keep the questions related to the topic. So let's get going. So actually, I wanted to start off with an acknowledgement in this case because, you know, we're all taught by somebody over the course of our lives and our careers, and that's especially true for this presentation. I want to thank Joe Ronalden. He might actually be on. Um, he's taught me a lot over my career, and I cribbed much of today's presentation from stuff that he's done before. So just so you know. And Joe officially is retired, but he still is active and he consults. And he does a lot of helping utilities analyze things when they fail. So if you got a cable or a fitting or just about anything else that's broken when it should not have, you could reach out to him. Here's his contact information. So, and there are other people that have taught me too. And in fact, one of them I'll mention in passing later, who I see is on. So to the topic, let's start with an easy question. If you're looking at an aerial system such as a transmission line, but it could be a distribution line or something else, what is it exactly that sags and what is it exactly that has tension on it? So I'll give you 2 seconds to think about that in your mind. And if you answered the conductors, OPGW, ADSS, you might generically answer whatever the cables are or the wires or anything along these lines. Well, all of the above are correct. Okay, but don't get too far ahead of yourselves because the questions will get harder as we go through this. There are lots of different types of conductors used in aerial cable systems. Here are some pictures of them. Just give you a moment to take in their beauty. And then if you may have noticed, amongst those cables that there are a lot of different types and styles, in particular, a lot of different materials. Here are some of them in no particular order. And then I mentioned the constructions. Again, in no particular order, round wires versus trapezoidal wires. You've got different sizes of the wires and or whatever other things are in the cable. I didn't show a single strand of wire, but that could be an aerial cable versus cables that are comprised of multiple strands. You got different numbers of layers of materials. And I threw an ADSS cable on there because it's a combination of plastic and aramid materials, but it's used aerially. So you could see that on some kind of an aerial cable system. Now, from an engineering standpoint, we could classify cables as homogeneous. So examples of these would include all aluminum conductor or all aluminum alloy conductor, AAC and AAAC respectively. They're a bimetallic homogeneous construction. So aluminum clad steel, which is often called alumaweld. Aluminum clad steel is the more general term. Alumaweld was actually originally a trademark from the company that invented that aluminum clad steel concept. If you got aluminum clad steel, no surprise, you got copper clad steel, commonly called copper weld. Galvanized steel. So traditional cables such as 3/8 inch HS or EHS or UHS, and there's also a utility grade out there somewhere, but galvanized steel cables. So you got two metals, but the cable itself is homogeneous in the sense that if you've got aluminum clad steel wire, all of the wires are aluminum clad steel wires. In contrast to bimetallic mixed construction, so two metals but used separately, so to speak. So aluminum conductor steel reinforced, ACSR would be an example of this. The core wires are generally galvanized steel wires, and then what's actually conducting the electricity are aluminum wires that are stranded over top of that steel core. But you've got others besides this. You've got aluminum conductor alloy reinforced, aluminum conductor steel supported, ACSS, previously called SSAC, and OPGW could be considered a bimetallic mixed construction because generally it's got components that are aluminum and then components that are aluminum clad steel wire. And then within these, you've got various variations, ACSR, AW. So ACSR, but instead of galvanized steel in the core, you have aluminum clad steel. ACSR trapezoidal wires, ACSR TW. And those previous calculations, you could say, are traditional. Today, transmission lines and other aerial systems use conductors with a combination of metallic and non-metallic components designed for high temperature, low sag operation. It allows you to operate a transmission line at a higher temperature and thereby increase power transfer. So if you threw those in there, you could create a fourth category, metallic and non-metallic combinations. And this high temperature, low sags, there are various uh, or implementations of that concept out there. You've got ACCR, ACCC, ACCS, C7. The idea here is just the variety of cable systems that are used in the world today. And of course, I'm the fiber optic cable guy, so let's not forget non-metallic cables, which would include all dielectric self-supporting, commonly known as ADSS. And then within the ADSS world, a very wide range of constructions, including different materials being used for strength. And we could also throw out there combinations of the previous lashed cable systems, typically a steel messenger cable that's supporting something else. And there's also spacer cable systems where, again, you have a steel messenger cable with a series of hangers that support something that's being used as a conductor. And I've left out at least two already, metallic aerial self-supporting, mass, which is kind of like ADSS, but it has some metal in it. Remember, ADSS, all dielectric, should mean no metal. So um, there's that. And then figure 8 cable. It's basically a lash cable, but it's integrated into a single cable. And I might have missed some others, but the point is these. There's a huge range of different types of cables that are used in aerial systems today. And these cables have materials that have different strengths, different moduli of elasticity, different densities, and different coefficients of thermal expansion. Plus, there's a wide range of construction, the different stranding configurations, for example, and the manufacturing processes vary from amongst all of these. So consequently, the different cable types are going to have different mechanical behaviors. And the behaviors of cables in an aerial environment where the temperature and weather, meaning wind and ice, are constantly changing is quite complex. So all of this may seem kind of simple so far. So you should be, though, a little bit concerned because of all this variety. So you ought to be at least a little bit worried. We'll see, but let's keep moving. Sag. So for much of this presentation, we're going to consider a single span from one attachment point on one structure to a second attachment point on a second structure like this. Fortunately, though, despite all of that variety of cables, the concepts that we're going to talk about today are going to apply regardless of the cable type. There may be some wrinkles, one cable type versus another cable type, but you'll be able to understand what those wrinkles are and why they are there. So here we go. Sag defined. Geometrically, sag is the vertical distance from a straight line between the attachment points. So you got two attachment points to a parallel line that is tangent to the cable. So we got our attachment points, this horizontal line, straight line between the two. Here's the actual cable. Here's that tangent line. This distance is the sag. In a level span, sag is always at the midpoint of the span. And we're going to, throughout this presentation, refer to that as mid-span. And it turns out that the low point, so the lowest point of the cable, is also at mid-span. And then just to make it clear, a level span results when the attachment points are at the same height, as you see in this illustration here. In an unlevel span, the sag, maybe this is a little bit surprising to you, but the sag is still always at mid-span. So it's always halfway between the two attachment points on this straight line between the two attachment points. But in an unlevel span, the low point is not at mid-span. And the sag at the low point is always less than the sag at mid-span. So here's your point of maximum sag. Here's the sag at the low point. So it's always less than the sag that's at midpoint. And as you can already surmise, you get an unlevel span when the two attachment points are at different heights. And so that could result from structures at different elevations. One structure is on a hill, the other structure is beneath it. So if the low point is not at mid-span, where is it? And the answer is that you have to calculate it. And on standard sag charts, which we will look at much later, I'll explain later, um, it won't be there. You'll have to find it. We'll come back to that in a moment. So let's go back and look at the two side by side. So in a level span, we have the sag at midspan. We have the low point at midspan. And the low point sag equals the midpoint sag. In an unlevel span, the sag, the maximum sag, is still at midspan, but the low point is not at midspan, and the low point sag is less than the sag at midspan. Now, I should note there is not always a low point in every span. So consider this hypothetical example, but it's a situation that does occur in the real world. So here's span 2, and you don't really see a low point. One could say that, okay, the low point is the lower attachment point. Yeah, okay. Okay. But you'll still see that the sag, the maximum sag in both, is still at midspan. So recall that I said that you can calculate the low point in an unlevel span. Here's the math to do that. Now, at first, this might look intimidating, but it's really plug and play. So you have your span length, you know your sag here. So the amount of sag at the low point is this formula, and exactly where it is within the span is this formula. Not too hard. Okay, so we've talked about sag. Now let's talk about tension. And I want to start off with, imagine that we have hung a chain from a single attachment point. The vertical tension at the attachment point is the weight of the chain. But then that means that the tension at the bottom of the chain is 0. And again, these concepts as we talk about tension are going to apply regardless of the cable type. So for the attachment point to remain stationary, the attachment point is providing the counter to the weight. Oops. And as I mentioned already, the tension at the bottom of the chain is 0. So if there's tension here at the top, that results from the weight of the chain, but there's no tension down at the bottom, that means that the tension is varying from bottom to top. Maximum at top, minimum at the bottom. Here's the variance, like an illustration of that concept. So now let's take our finger and imagine moving the chain horizontally from the bottom. Once we do that, we're imparting a horizontal tension in order to move the chain, and then the attachment point is providing a resistance to that. So that tension carries up to here and then is resisted by the attachment point. Otherwise, the tension would have to move. So that means that the horizontal tension is exactly balanced at the attachment point. No more, no less. So we still have the weight of the chain to contend with. So effectively, we end up with a resultant tension. It's the interaction of the force from the weight plus the horizontal tension. Mathematically, that's the resultant tension is the weight plus, oops, this is a mistake. This is supposed to be the horizontal tension. Can't fix that right now. But anyway, sorry, didn't notice that before. So again, the attachment point is resisting effectively the resultant tension. which is to say both the weight and the horizontal tension. If we continue to pull on the cable, we're increasing the horizontal tension and we're increasing the resultant tension as well. So now let's fix both ends of the cable and let's see what happens. We have our level span back, and then what we find is half of the weight of the cable is supported at one attachment point and the other half is supported at the other. And you see here we still have our horizontal tension and our resultant tension. What if we don't affix them both at the same height? Well, if we do a fully inclined span, meaning with no low point, all the chain's weight is supported at the higher attachment point. What if there is a low point? Well, then the weight will be proportionally divided between the two supports. So you'll recall this illustration from before. You can find how much weight is at the lower attachment point by calculating this. And at the upper, once you know this, you also know this distance from the structure that's higher uh, to the low point. And this becomes a reason why you should know how to calculate where the low point is so that you can decide, or excuse me, determine how much weight is at each structure. So if we go back to the level span, we can make a couple of observations. One is that there is no significant weight at the low point. That's because it's all at the two attachment points. So you could take your finger and push the cable at the low point and move it just a bit. Yeah. And recall that the tension varied in our vertical hanging chain. So that's going to lead to the second observation, which is at midspan, there's only the horizontal tension. There's no weight from the previous observation, and there's no resultant tension there either because there's no weight there. There's only the horizontal tension. But at the attachment points, you do have the horizontal tension, the weight, which in turn leads to this resultant tension. So we have looked at the basic concepts of sag and the very basic concepts of tension. And now we're going to look at the relationships between the two. So our level span again. So we have our sag and we have our horizontal tension. And in a level span, sag is going to be generally inversely proportional to the horizontal tension. So what that means is if we increase the tension, we decrease the sag. Or conversely, if we decrease tension, we increase sag. And there are exceptions, which we're going to consider later. Now, the flip side of what we just talked about is also true. So if we increase sag, we decrease tension. If we decrease sag, we have to increase tension. Again, those same exceptions that were mentioned before, we'll see later in the presentation. So to sum that up, horizontal tension is generally inversely proportional to the sag. Plus, let's again note, at midspan, there's no weight acting on that point. The weight is supported by the attachment points. I recognize that this is not intuitive. It doesn't even seem like common sense, but it's nevertheless true. Now, What about temperature changes? As cable temperature increases, the cable material expands, which causes a cable to elongate. When cable length increases, the sag will increase too. It has to. It's the only possible outcome. And the tension will decrease. So going back to those previous relationships, sag increases, so tension has to decrease. This is only thinking about cable temperature, not wind and ice loading. We'll think about that later. So conversely, as cable temperature decreases, the cable material contracts, and then that means that the sag will decrease and the tension will increase. These are generally true. There are exceptions that we'll discuss later. So recall that we said a long time ago now that different materials have different coefficients of thermal expansion. Didn't define what that was before. Now we'll define it here. The coefficient of thermal expansion is a material property. It's expressed in units of per degree Fahrenheit or per degree Celsius. And this coefficient indicates how much a material expands or contracts in response to temperature changes. So using this coefficient, you can actually calculate the amount of expansion or contraction for a given temperature change in a cable. Now, we're not going to actually do this today. You just need to remember that you could do it if you needed to or wanted to. So just because we're not going to actually show how to calculate it doesn't mean we're not going to talk about it, though. So general guidelines for metallic cables are that metals expand or contract a lot, relatively speaking, to non-metallic materials. So metals can expand or contract a lot in response to changes in temperature, again, relatively speaking. So what that means is you get a lot of change in sag and tension with changes in the temperature of a metallic conductor. And it becomes no surprise, therefore, that thermal effects or consideration of thermal effects is a significant factor in the design for conductors because conductors are affected by both environmental temperature changes, you know, cold in the morning, hot in the afternoon, for example, plus the temperature increase that's caused by current flow. So flow going through a conductor will heat the conductor up. So therefore, a lot of change in sag and tension. So for non-metallic materials, so plastic and maybe not all, but many non-metallic materials, they expand or contract only a little. We're talking relatively speaking again in response to changes in temperature. So you have low to no change in sag and tension to the point that it may be surprising to you, but should only be a little bit of a surprise that thermal effects on ADSS are so low that they're generally completely ignored when making sag and tension calculations. And we did mention high temperature, low sag uh, conductors earlier. These are possible because of the low thermal expansion properties of the composite materials that are used in their cores to carry the weight of the aluminum, which is carrying the current on them. Next up, the effects of creep. Creep is the permanent stretching or elongation, that's the term we're going to use, of a material under tension over time. We say it's permanent. The technical term that's used is it's plastic, not as in plastic like the material, but when you're in the realm of materials, people use the term plastic to say it's a permanent elongation or deformation, deformation of a material versus an elastic stretching. So we'll see this in a moment. I'll define this more clearly. So as the cable creeps, it's elongating over time. The length cable length is increasing, that means that the sag must increase. And then we know that if the sag increases, then the tension will decrease. There we go. So I started to define this on the last slide, but I had put it here. So plastic refers to permanent elongation. So the elongation remains even if the tension is decreased to zero. So you've applied some amount of tension, it's permanently stretched the material. And the opposite is elastic for elongation that is only temporary. So you apply tension, the material stretches, but you remove the tension and the material contracts back to its original shape. So most materials can endure some tension with elastic elongation. It may not be much, but they can endure some tension with elastic elongation. And once you're past that point, the elongation becomes plastic. So, aluminum in particular it is this way. A certain amount will recover. You go past that point, it doesn't recover anymore. If the tension continues to increase after reaching the plastic point, well, eventually you're going to get to the point where the material just breaks. More observations about creep. Aluminum conductor under tension for 10 years will stretch to about 97% of its maximum creep elongation. So because of this observation, it's generally taken that after 10 years of hanging in the air, a cable has reached its maximum elongation. So we say it's reached its final condition. 10 years is commonly used in sag and tension calculations as the basis between initial, so as you originally installed a cable, and its initial sag and tension, and the cable's final sag and tension. So we keep using the word generally. Uh, yes, I say that because creep can vary depending upon the actual loading that a cable experiences during its operation. However, so in other words, maybe this maximum point could be reached before 10 years, or maybe it's after 10 years. The truth is you never know in the under field conditions. You just never know. Did it get there before? Did it get there after? You just don't know. You don't have any way of knowing, practically speaking. Nevertheless, you can say that there's a limit to the maximum elongation that you can get in a cable. So the actual loading conditions in the field might make creep go faster. So if the loading was higher than you thought it would be, or it might slow it down if the actual loading was lighter than you thought it might be, but you still end up in about the same place. So effectively, this 10-year um, rule or practice, it works well in reality, even though you don't know what's really going on in the field. So here are just a couple creep test results. You can go to a lab and do a creep test on a cable and find out how much it's going to creep. This is an OPGW cable because remember, I'm the fiber guy, so I had fast access to OPGW creep test results per the IEEE standard. And the IEEE standard, you are testing for 1,000 hours, and then you can project the performance out to the 10-year standpoint. Here's a creep test for an ADSS, basically the same test. But notice we'll see in a minute, there are some significant differences between the two. So first observation, creep is progressing logarithmically. Look at the scale below. The time in hours, this is a logarithmic scale. Notice that the creep of the metallic OPGW is about 0.15%. So we started here and we end up after 10 years, we end up about 0.15%. But the ADSS, non-metallic, ends up at almost 2%. 1.8. Uh, the test ends, I'm sorry, the test ends at 1,000 hours. The projection ends at 10 years, somewhere up here. We're close to 1.8%, almost 2% in the ballpark. So over my career, I've observed that a rough guideline for creep in metal cables is about 25% of the creep elongation occurs in the first 2 days after installation. You get about 50% of the total creep. So if you look at, you get about 25% after 2 days. You get about 50% after 2 months. You get about 75%. So now you're up somewhere over here. After 2 years, and then 10 years is 100%. I meant to go back and convert these into hours because then you could see it directly on this time scale that you do indeed end up about 25%, 50%, and 75%. It's a rough guideline. It's helpful in some cases to know about what it might be. I refer to this as the 2-2-2-10 rule. And again, any metallic cable. Haven't looked at it for ADSS, quite honestly. Not sure if it's true or not. Okay, enough about creep. Now we're going to talk about aerial cable behavior, and we're going to start off with a catenary. A catenary is the curve that a hanging chain or a flexible cable assumes under its own weight, where the weight is uniformly distributed along the curve, right? So the cable's weight is uniformly distributed along it. And the cable, or in this case, the chain, is supported only at its ends. Looks like a nice smile, doesn't it? So the word itself comes from the Latin word catena, which means chain. Here's an example. Now, the last caption said an example in nature, a little bit of a joke, but it really does, you really can find catenaries in nature. Here's a picture of a spider web. Notice the nice catenary shape, and notice the attachment points are not at the same height. So this is an unlevel span, but we still find the maximum sag is at midspan, and we find our low point as well. And notice that its sag would be less than the sag you get here. Really, it's true. So here's the math behind a catenary. A catenary curve is a graph of a hyperbolic cosine function. And this is taken from the electrical engineer's handbook from long ago. Here's the formula. I just want to pause here for a moment just to take in the beauty of this math. If we then plug in the variables for an aerial cable span, we get this version of the formula. So our sag is equal to our horizontal tension divided by the cable unit weight, the unit weight pounds per foot. Hyperbolic cosine, I just get a tingle in my spine when I even say the word hyperbolic cosine. Oh shoot. This should be the unit weight. So WC divided by the horizontal tension plus the span over 2 minus 1. Wow, it's beautiful, isn't it? Now, you know, I don't know about y'all. I I love solving a hyperbolic cosine function every day. And today with computers, it's easy, but that's not always been the case. When I was little, uh, w- our math aid was counting using piles of small rocks, like you see in the picture there. And then the abacus was a revolutionary invention, for me around middle school. And then the slide rule, which, my memory is a little fuzzy these days, but I'm pretty sure that came out about the time I was in high school. And they're amazing. But even using a slide rule, it can be a little bit tricky to calculate hyperbolic cosines. So fortunately for us, the old wise ones of transmission line design figured out that using a parabola was easier than using a catenary. And a parabola describes the shape that is assumed by the suspension points on a cable that supports horizontally distributed weight. So here, the weight horizontally is is here, distributed horizontally, whatever it is this cable is supporting. These are the suspension points. Again, resembles a smile, so it's very welcome, warm, and welcoming. And in case you're wondering, the cable between the attachment points, it's still that catenary shape. May not look like it at first glance, but it's true. Parabolas, again, we find in nature, or banana here, for example. And man-made parabolas exist. So here's the Golden Gate Bridge as an example. And by the way, I happen to know that this bridge is for sale. So if you're on Venmo or Zelle and you're interested, reach out to me after the webinar. I'll, I'll take care of you, so to speak. And now here's the mathematics of a parabola. So parabolic curve is a much simpler equation, y equals x squared. If you plug in the variables for an aerial cable span, you get sag equals the unit weight times the span squared divided by 8 times the horizontal tension. A lot easier to calculate. That does then lead to the question. So it's great that it's easier, but how much accuracy do you lose using a parabola? Well, the rule of thumb is that when the sag is up to 6% of the span length, the error is less than 1.5%, 1/2% too small. So a little bit less sag. The calculation will tell you the sag is going to be a little bit less than what it actually will be. But that error is typically less than whatever the cable's diameter is. So we'll actually do that. So I'm sorry for those outside the United States. I've only done it in customary units today. So here's a 1590 kc mill, 45/7. So the strand configuration, 45 aluminum strands over 7 galvanized steel strands, ACSR, diameter about 1.5 inches. Here's the unit weight. Strength is about 42,000 pounds. Um, Realistic sag and tension calculations for this cable on an 800-foot span, you would get the initial tension right after installation at 60 degrees Fahrenheit would be about 18% rated breaking strength or 7,600 pounds. The final sag at 212 would be 29.7 feet with a horizontal tension of 4,835 pounds. Uh, you kind of have to take my word for it that the sag and tension calculations would give you a sag chart with these values. So the parabolic sag calculation based on the horizontal tension from that sag chart is this. The math, very straightforward. Final answer, 29.65. But the sag and tension chart, which is using the catenary format, gave you 29.7. So you see you're half an inch less sag than what it's actually going to be. So the parabolic approximation, pretty darn good. So some additional comments based upon the example. So that amount of sag is 3.7%. So that fits within this rule of thumb. You know, don't use this if the sag is more than 6%. And the rule of thumb said it was going to be 0.5% too small or up to 0.5%. So our actual error is well within the expected error allowance, so to speak. And that actual error, again, much less than the conductor diameter, in this case, less than half of the cable diameter. So as I said a moment ago, the parabolic approximation is pretty darn good. And in fact, if you view that error in context, in the field, in the real world, it's probably the smallest error that you can consider. So there's huge error in estimating creep. As I said earlier, you don't know the actual history of temperature changes, tension changes, and ice and wind and loading changes during the cable's operation especially not over 10 years. There's also error in stress strain curves. There are a lot of reasons for this, which I do not have time to discuss today. I've already made reference to a follow-on to this. We will talk about that, the follow-on presentation on this, just don't have time today. The largest source of error results from field installation techniques, and in particular, how cables are sagged. Again, another time. This is just a reality. These are the big three sources of sag error in the field. I call it here parabolic error, but it's really sag error in the field. And there are others as well, but I don't have time to go into it all. Instead, I have to move on to those exceptions to the sag and tension relationship that we talked about earlier. Recall that we said that in a level span, sag and tension are generally inversely proportional. So increase tension, you decrease sag, or if you increase sag, you're decreasing tension. There are three exceptions to this. One, when ice accumulates on a cable, it adds weight, which in turn stretches the cable or elongates the cable, which thereby increases both sag and tension. Remember, it should be that if you increase sag, you decrease tension, but instead we're going to be increasing both. Similarly, when the wind blows transverse to a span, so across a cable, it imparts a force, which again stretches the cable and again increases both sag and tension. And then no surprise, you can combine the two. So let's look at these quickly. When ice accumulates on a cable, it's adding weight and it increases both sag and tension. So when it's just ice, no wind, the increase in sag is all vertical. No surprise. So here are your values for your horizontal tension, your weight, and your resultant tension before you apply the ice or before the ice accumulates, and they all increase after the ice accumulates on the cable. Effective wind loading. So prior to this, we've always been looking at a span where you're looking across the span from left to right. Now, you've turned it 90 degrees. Now the attachment point is beyond this point, and you're kind of looking at the second attachment. So here, the sag of the cable with no wind, the wind blows across and it causes the cable to blow out and stretch at the same time. this angle is the blowout angle, you can calculate how much it will do this. And so you've effectively got um, some of the sag is vertical and some of it is horizontal after the wind has affected the cable. And then you have both ice and wind. Basically, it's a repeat of just the wind, except the additional weight to the ice is going to increase the sag even more. So they'll work together to, in effect, increase your total sag. So keep in mind that the effects of ice and wind should also be viewed in conjunction with changes in temperature. In other words, when you've got ice on a cable, it generally means that the temperature has dropped. So that makes this relationship more complex. We were just looking at things in isolation, only the application of ice. But in reality, temperature change is likely going on. So in a metallic cable, you're going to have decreased temperature. That's going to decrease the cable elongation, which in turn decreases the sag, which increases tension. But the ice is increasing elongation and it's increasing sag, uh, uh, decreasing tension. So there's a conflict here. In general, elongation would increase sag and decrease tension. Um, how's this going to work out? Well, you don't know. So it depends on the details. You got to run the calculation. And then for a conductor, you've also got to factor in the thermal effects of heating caused by the current flow. So again, you can't say. The heating might counteract the environmental temperature change, or it might not be enough to do that. So you end up having to run the math. And then what about ADSS? Well, we already said temperature effects are generally ignored. So you only have to worry about the ice loading itself. So that's that. So, looking at the time, uh, I'm sure that by now your brain is full. My voice, I can tell, is on the edge, and, and our time is basically up. Yeah, we're about where we ought to be. So, we've done the basics today, and we're going to have to look at more later. So, look for an announcement with the date and time. We'll do something in August. And for today, oh, I didn't actually mention that. So in the follow-on session, we're going to look at SAG charts. I thought I said that somewhere. Obviously I didn't. So to recap today, what we've done is we looked at SAG and its relationship to the low point in a span. We've looked at what tension is. We've seen the everyday relationship between SAG and tension and the three exceptions to it. We've reviewed creep and how it changes sag and tension. We've looked at a catenary and how it relates to sag and tension. We've looked at a parabola and why you might use it in lieu of a catenary. We've looked at the approximate error in sag using this parabola instead of a catenary. We've identified the big three sources of sag error, and we've considered the difference between elastic and plastic changes in a cable's length and how those would affect sag and tension calculations. So that's a lot for one session already. So as I say, we'll pick up next time and we will talk about sag charts and sag coefficients and maybe more if I can fit it in. So look for that in the future. So some follow-up information. After this, thanks for your participation today. You will receive a follow-up email. It's going to give you a link to the video and the actual presentation. You can download the slides, a link to the quiz if you want to get the PDH credits, and also a link to a survey to give us feedback, including suggestions for topics that you think we ought to cover. About the PDH credits, to receive them, there's a quiz. You have to take the quiz. You have to pass with 70% or higher. Please do allow time for the process and to get processed, and then you'll get a notice that you got your credit hours. If you got any general questions, reach out to Alexis at marketing@incabamerica.com. And now, what questions do you have? We will attempt to increase ice or to unmute your mic. I don't know how increase ice came out of my mouth there. Or you can type questions in the chat. Hey, Joe Ronaldo's on. Thanks, Joe. And thank you for the compliment, Joe. I really appreciate that. Oh, I think someone wants to take me up on my offer to sell them the Golden Gate Bridge. I think I'm being offered 4 wooden nickels for it. Well, if you can send them through Venmo, that's great. Increasing ice increases sag, and the slide said decreases tension. Yeah, I think I screwed something up. Let's go back and look at something. Okay. In metallic cables, decreased temperature equals decreased cable elongation. So you're decreasing the sag, which increases the tension. But the ice is increasing elongation, which increases the sag and increases tension too. So I don't know why there's not a conflict there, because we said that back here. Right? Adds weight, increases both sag and tension. Changes in temperature. I don't know why I thought there was a conflict in here. This is a mistake. Oops. Which I can probably, I'll edit before we post the slides. There was another minor mistake that I'll get fixed. Vertical portion, increasing ice. That's the vertical portion of the tension. Well, a thing about this is that everything is still in the same vertical plane. So it makes this easy. It's here that things get more complicated when there's wind involved. Okay, somebody said they loved the presentation. Thank you very much. Have you thought about doing a session on galloping? Yes, I have. I will do a session sometime soon on motion control. I am debating if I need to split it up and do aeolian vibration and galloping separately, but I will do those. So the question is time. How much time does it take to cover both topics, and can I do them both justice in an hour? My sense is probably not. So I'll probably break them into one on aeolian vibration and a second session just on galloping. So, okay. In OPGW cable, does the strain of fiber need to be controlled? Yes, absolutely. I've, this we're talking about sag and tension, so I didn't want to get into things like that, but I do cover that in other presentations, most notably the loose tube design concept presentation on that. So if you go to our website, you can see all of the topics that we've covered. Look for the one that talks about the loose tube design concept. And that will give you guidelines on how fiber strain should be controlled. There's also the OPGW Engineering 101, which will also give you insight as to what the fiber strain might be in a particular cable type. Yeah, it still helps. And then when I did the sag and tension one, that one too had OPGW sag and tension calculations. I did talk about how you would do the calculations and look at the strain and what the strain some guidelines on strains would be. So you've got three sources there. Uh, is it of concern that aluminum doesn't have a fatigue limit? It will fail as and at any stress level, it will fail under a certain number of cycles. In conductors that are not all aluminum, or does the reinforcement of the core of the cable make this not a major concern? Well, I, my mind is hung up on the first sentence. Is it of concern that aluminum doesn't have a fatigue limit? It does. It has a pronounced fatigue limit that's much lower than steel. So normal sag and tension changes, like just from environmental effects, just the daily expansion and contraction, and due to temperature changes, and for now I'll call it moderate changes in wind conditions. Um, you're not likely to fail a cable from anything like that. What you are likely to fail a cable from is aeolian vibration. And that's just because that takes the cable changes uh, like a factor of 1,000 greater than just normal everyday kind of changes. So you do have to be concerned about the fatigue limit of the materials. In the real world, what it generally works out to is that the aluminum is the one that causes you trouble. And so when I do the presentation on aeolian vibration, you'll understand that. I'll explain that in more detail. So for normal type operations, um, it, just as I say, normal everyday type fluctuations, not a concern. The concern is what happens when you get aeolian vibration, because that can quickly cause materials to fail. Uh, yeah. Okay, good. I'm glad I answered your question. Um, other questions? See? Okay. Well, I appreciate everybody's time and attention today. Um, again, look for we'll send out a notification about the next session. We're going to go into more detail with SAG coefficients and SAG charts. And then, as I say, later in the year, I'll also do one or possibly more likely two sessions on aeolian vibration and galloping. All right. Thanks again. Hope you enjoy the rest of your day, and we'll see you next time. Take care. Bye-bye.